All right, so we're in 10.7 now, second to last section for this class. And my personal opinion on 10.6 and 10.7 is that they didn't really need to be two separate sections. I feel like each section by itself is not terribly long, and they cover essentially the same topic, parametric equations. It's just the focus here is more on graphs. I think they could have easily made this one section, and it wouldn't have been a problem, but nevertheless, we're in 10.7, and like I said, this is a relatively short section because it's just completing the work that we did in 10.6. So anyways, what we want to do first is graph a curve that's given by these parametric equations: x of t equals t squared plus 1, y of t equals 2 plus t. And this one is an example that showed up in your book. I'm using the table and the graph that they came up with. Just because the graphics were, I like the image here, so that'd be difficult to recreate by hand. I'm not very artistically talented. Anyways, the idea, like we've seen before, is to just plug in values of t into a table to see what x and y would be corresponding to each value of t that you plug in. That gives you a set of ordered pairs that you can turn into points and plug into or plot and then graph the curve that passes through those points. So this graph shows a little bit more than you really need to show, but I like the extra detail. So you notice the graph that we ended up with looks like a parabola. And you would have started by plotting the points that you get in this table. And what they show here is not only the labels for the points, but the values of the parameter t that give us each of these points. You see like a t equals -3, t equals -2, t equals 1, and so on. You don't need to write all that stuff in when you're doing your graphs, but what I like about that is that it makes it easy to see the orientation of this parabola, because t is increasing as the points go this direction around the parabola. That gives us this orientation, which is shown by these arrows. And generally with parametric equations, you want to show that orientation in your graph. So let me do a couple more examples of graphing. Now this is one way to approach graphing parametric equations, and it's totally valid. The problem with it is it's just a lot of number crunching because you're putting a lot of data into a table. And you could argue that you don't need this many points to get a good graph of that curve, but even still, if you only did like 5 values of t, which I wouldn't do any less than that if you were doing a table, it's still kind of a lot of number crunching. So what we'd like to do is use the method that we came up with in 10.6 of eliminating the parameter to put the parametric equations into the form of a single rectangular equation that looks familiar, something that we recognize. Now in this case, in order to eliminate the parameter, this looks kind of similar to our unit circle example in 10.6, but it's not. If this were a cosine of t and this were a sine of t, then I could show that this parametrizes the unit circle. But the cosine squared changes that. So how do you eliminate the parameter here? Well, I have x equals sine of t, and I have y equals cosine squared of t. The goal here is to make some kind of substitution. Well, I know from my Pythagorean identity that cosine squared of t is the same thing as 1 minus sine squared of t. Now, I have a sine of t here and a sine squared of t here. Actually, I don't know why I put my second power there. Squared should be right there. That means I could substitute an x for the sine here, giving me this, y equals 1 minus x squared. Okay? So the graph of this is going to look like the parabola y equals 1 minus x squared. That's a parabola that has a y-intercept of 1, that's where its vertex is, and it opens downward because the coefficient on my x squared term is negative. So this would be -1 here, and this would be +1 here. Okay, now it turns out that's as much as the parabola that I'm going to be able to graph. And this is something that's important to be paying attention to when you're graphing parametric equations. Even though by eliminating the parameter, I ended up with the equation of a parabola. There's a restriction on this thing that I wouldn't really have caught if I wasn't paying close attention to my parametric equations. You see, the sine function has a range of -1 to 1. And so if x is equal to sine of t, then x can only take on values between -1 and +1. Similarly, y is equal to cosine squared. Cosine takes on values from -1 to 1, and then if I square that, that gives me values between 0 and 1, because squaring those values gives me non-negative numbers. So the y-coordinates of this graph can only be between 0 and 1. So that means I can't do any more of the parabola that goes below the x-axis, because I would end up with points that don't actually belong to the original curve. So that means that my parabola is just this little, or my graph is just this little piece of the parabola. Now, how do you deal with orientation? Well, you could start by plugging in a couple of values for t. For example, plug in a 0, then maybe plug in a pi over 4, and then plug in a pi over 2, and so on, and see which direction the orientation of the curve seems to take. The problem with that, though, is that because this curve it has a start and an end, depending on which one you want to call the start and which one you want to call the end, the orientation's not consistent. What I mean by that is if you plug in lots of values for t, say plug in, t equals 0 all the way through like 4 pi or something like that, you're going to see that the points trace out this little piece of the parabola and just bounce back and forth. So sometimes the orientation appears to be this direction, sometimes it appears to be this direction, and because it's not consistent, we can't write in the orientation for this curve. Okay, so that will occasionally happen. You just have to be paying close attention to the original equations that you're given. Let's do another example. I want to graph these parametric equations. X equals e to the t, y equals e to the 3t, and remember we can do this. E to the 3t is the same thing as e to the t cubed. We do this because this allows us to make a substitution. Y is equal to x cubed. Okay? So then if I were to go and try and graph this, cubic functions look kind of like almost like an S sort of a shape, but we want to be careful here as well. It turns out that the graph of this equation, or these parametric equations, will only look like this. And the reason for that, notice the points that I'm using are only points in the first quadrant. That's where the x and y coordinates are both positive. And the reason that is necessary is because x and y are both defined using exponential functions. Exponential functions only take on positive values. The range of e to the t is the set of all positive real numbers. In fact, you can't even make it equal to 0. There's no value I could plug in for t here such that e to the t is equal to 0. And that's why the origin's not included either, because that would imply that the point 0, 0 is on my curve, and we know we can't get that. So the curve looks like this. Now, what's the orientation? Well, it seems intuitive that the orientation would be moving away from the origin, but if we want to verify that, we just need to pick a couple of values to plug in. So I'm going to make a small table for my graph here, and just plug in a couple values of t, maybe 0 and 1. So if I plug a 0 in, e to the 0 and e to the 3 times 0 are both equal to 1. That corresponds to the point 1, 1. So if 1, 1 is right here, that corresponds to the point where t is equal to 0. What about if I plug in a 1? Well, if I plug in a 1, e to the power of 1 is e. That's approximately 2.7. So e is going to be further out. And then if I plug a 1 in here, that becomes e to the 3rd power, which is, this is not to scale, by the way, but it's going to be up here somewhere. So my scale's way off, but let's just say it's here. T equals 1. So I can see that as t increases, and it would not be here because of where I drew my e, it's going to be off the curve somewhere, but I need to be able to put something down so I can see what I'm working with. As t increases, the point seems to be going this direction, so that's my orientation. Okay? So you can see eliminating the parameter makes it so we don't need to worry about making these large tables to determine what the graph of a parametric equations look like. You can do this still. There's no rule saying you can't, but oftentimes the more efficient method is going to be the preferred one. So this is a couple of examples of graphing parametric equations. Last thing we want to look at in this section is an application of this to projectile motion. So your book gives you these equations for the projectile a motion that's been for an object in motion that's been launched like a projectile. So we're going to do an example where there's like a batter hitting a baseball. But here's the basic idea. Let's suppose let's make this x, make this y. Let's suppose the x-axis represents like ground level. And let's suppose a projectile is launched from some height above ground level, and it can also equal it can also be at ground level, in which case this h here would equal 0. But to keep things general, we can also give us some height above ground. If you launch a projectile, we know just from kind of an intuition, and there's science behind this as well. Oops, sorry, 1 second.